Okay, so hello everyone. I'm Thomas. I work at D&G Technology Consulting. It's a small company in Munich, and we are medium-sized meanwhile, and we do whatever the customer wants, develop software for them. So usually it's not Perl. At the moment I'm doing Java EE. But in my previous project, it was a Perl project, and there we managed to kill some SSDs, and that's basically, this talk is the war story about that. So that doesn't work. Or maybe I should turn it on. Better. Okay, so first of all, yeah, what is an SSD? You all know that. So an SSD is memory. So we want to store something. It's non-volatile, so it should retain the data if we turn the computer off. And it has no moving parts, so no spinning disks. And if we look into the history of SSDs with this definition, we will see, so that's what we cannot talk about. We will see that SSDs, by this definition, are around since the 50s. Actually, magnetic core memory, which was at this time used as random access memory, is an SSD because you can turn it off and it still keeps the data, and it has no moving parts. And so how does it work? One bit is stored in one of these metal rings by magnetizing them. And yeah, so I'm a bit short on time, and so I won't go into details how it exactly works. But yeah, you can read that at Wikipedia. So skip ahead 20 years. We have EPROM. It's electronically programmable read-only memory. So it's a bit a conflict. So it's read-only, but you can program it. So you program it once, then you can read it, and you cannot program it again until you erase it. And this is also the first semiconductor-based read-only memory. So in contrary to the magnetic core memory you had before, to erase it, you have this window on the top, and you have to illuminate it for 30 minutes with ultraviolet light in order to erase it again. So that's not really what you would use as like a disk where you want to modify data often. But the technology inside floating gate field effect transistors, it was already the same technology that now we have in regular SSDs. Then magnetic core memory, we already saw that. It's not that. So in 1976, a company actually sold magnetic core memory, lots of magnetic core memory, as a replacement for spinning disks. And the product you see over here, it's I think 2 megabytes of storage. You had to pay almost $10,000 for it, but they claim to be 5,000 times faster than the fastest spinning disks at that time. So depending on your application, it might have been worth money. So then again, 1 year later, EEPROM, or maybe, I'm not sure if I'm pronouncing that correctly, and there is a new letter inside, and that means erasable. So it's electronically erasable programmable read-only memory. And that was a huge step forward. So that's the guy who invented it. He was also later the founder of SanDisk. And now he got rid of this window on the top of the chip where you had to use ultraviolet light to erase the flash memory again. So you could do that electronically, but still erasing was much harder than writing to it. So it needed more effort, a higher voltage. It needed you usually erase larger blocks than you write to, and it needed more time than writing to it. So it was still rather
you needed to take the chip out and put it somewhere else to erase it.
Sorry.
You needed to take the chip out to erase it.
Okay, also for the electronic. Okay, I didn't know that. So it was still rather like you could reuse them or reprogram them, but not like on the fly. And then flash memory was invented. What this guy did, he worked at Toshiba at the time. He had the idea that you should optimize the erasing, because the erasing was what made it slow. And his idea was to erase much larger blocks of data than the block size for writing to it. And this way he got rid of disturbances between neighboring cells when erasing, and he also sped it up because it's way faster to erase one block at once, one big block at once, than many small blocks at a time when you need them. And yeah, as I said, Toshiba was he worked for Toshiba, but they were not interested in this. So he presented his idea in the States, and so SanDisk built the first flash-based SSD. It was had a size of 20 megabytes, and it was it was about $1,000 at the time, and it was actually used in regular laptops. So much for the history. Now, how does it work? Like, to understand how we can kill an SSD, we need to understand the atomic unit of memory in an SSD. It's the floating gate field effect transistor. So, any physicists here? Oh, I'm the only one. Okay, so it's quite simple. You have in principle a regular transistor. So if you apply voltage to the control gate, you can then control if current flows between source and drain or not. But you also have a floating gate in the middle. Floating means it's isolated. It's not connected electrically to anything, to any component. And if you put electrons on there, then it behaves the same way as you would charge the floating gate. So you can, and then the transistor blocks the current. And so that's how you program a floating gate field effect transistor. Erasing it is different. So to program it, you apply positive voltage here and between here and here, between source and control, and then or you can also apply current here. So you have hot electrons that have that can more easily go over this barrier, and then you can charge it. To erase it, you need to do the reverse. You need to apply a high voltage, a high negative voltage between here. So electrons here, no electrons here, and then you can put them out again. But it's more difficult, and you also have to take care not to. Like I said, it affects larger portions of the chip. So usually you erase a large block, and this also implies that you cannot randomly read and write cells. You always have to erase them first, and if you want to modify data in place, you cannot do that. You write them to another block and erase the old data later. What also happens here is that in this isolator, damage is done while erasing and writing. So you damage the chip by the read, not by reading, but by the erase write cycles. And that's the the origin of all the problems we had later. That's just short to remind you that the flash memory is only a part of the SSD. You have, of course, some infrastructure around, some logic that it looks like a spinning disk maybe to the host, and some other stuff you need. So, what's the current state of the art? I have to warn you in advance, this is already outdated again, because the Flash Memory Summit took place this week, and all the numbers I present are probably obsolete by now, but that was the state of the art like a week ago. So that's the one I have in here. It's a consumer SSD, 1 terabyte, and you see it's mostly air. And inside here, those 4 chips have all the memory. So if you open up one of the smaller ones, it's even the chip only goes up to here. So it's a big chunk of air, and but it works. So now let's look at 2 enterprise SSDs. This one is the last week's biggest one. They had. It's 50 terabytes and it has the form factor of a regular 3.5-inch disk. So we'll see later that the biggest regular spinning disk you can buy at the moment, as far as I know, are up to 10 terabytes. So SSDs have a big advantage here already. And I think this 50 terabytes is already obsolete again, because from the news I got from this Flash Memory Summit, I think they doubled it. Another company put some. It's not this format, but you can put it in a like this one. You can put it just on the main board, and it has, I don't know, over 100 terabyte. So this one was optimized for size. This one is optimized for speed. From this company, Fusion.io, they were bought by SanDisk, obviously, and we can just look at the specs maybe. So we can also talk about the price. So this one is $300. This one is the one optimized for speed. It's $54,000. So it's really expensive, but it may pay off. For this one, they didn't even put a price tag on, but they're already selling it to some people they should probably know. And yeah, that's just for comparison a regular spinning disk. Also enterprise server disk, but maybe more reliable, and should be quite fast compared to others. It's also okay. And now let's just look at some of the numbers here. So first of all, capacity. Okay, we already had that. SSDs have a clear advantage if you optimize for it. You don't need to. You can also, if you want speed, you probably should rather stick to a model like this. And we see here while the serial read and write bandwidth is still comparable to a fast spinning disk, where the SSD is clearly an advantage is random access. So random reads, random writes to just somewhere on the disk. Yeah, we will see later why that it is that way, but we see here we have no chance of achieving such a thing with a single spinning disk. We could use a cluster maybe, but then we would also have to be lucky that all the data we want is on different disks. So we have to combine random read IOPS. IOPS, by the way, is I/O operations per second, if you wonder, and yeah, that's about the things we can compare to the spinning disks, but there is another line on the bottom here. It's endurance. Endurance is the total volume of data you can write to the SSD until it's worn out, until it doesn't work anymore. The unit here is terabytes written or petabytes written. And sometimes it's also specified as drive writes per day, so you can just write once, overwrite the whole drive once a day, and you do that for n days, and then you have like the same value in another unit. And usually, if you have something like this in your laptop, there's no way you're ever gonna write 150 terabytes until the laptop is broken anyway. So usually you don't get close to that. But there are situations where you do. We will see that later. And okay, I think let's skip over this one. So when to use SSDs? We already told you about random access. Access times is also an interesting performance indicator. On spinning disk, you are physically limited by the moving parts. So you have to wait until the read head has its right position. You have to wait until the sector of the disk actually containing the data spins by. And on average, with 15,000 rounds per minute, you are at 2 milliseconds alone for the rotation, and then you also have the seek time. With solid-state drives, obviously you don't have this problem. Okay, let's skip over this one. I'm a little bit late on the time, so just we can have a look at this. So still, SSDs are more expensive. So these are the consumer prices. So the enterprise SSD are still even more expensive. So if you're only optimizing for gigabytes per dollar, you might not want SSDs yet. There's, for example, Backblaze, this company that just puts thousands of spinning disks in racks to sell cheap backup space. But if you have some performance requirements or some maybe maintenance requirements that help you, then you should probably use SSDs. So it depends, as always. You don't want to use SSDs for everything. So now, how to actually write an SSD to that? That was our project. We did this, and just focus on the important part. We had 150,000 updates per minute on a MySQL database. So, and they were random. So it was not, we were not sequentially appending data on the end, but we were randomly updating things on that. And yeah, our setup consisted of 2 Fusion.io cards in a striped array. So to use twice the space, and they were specified for 4 petabytes written. And after 9 months, the performance degraded in production. So yeah, we looked a little bit around and found out, oh, nearing reserve space wear out. That actually means that most of the cells on most of the blocks on the SSD were already worn out, and the disk started to shift blocks around to this called wear leveling. So it moved when a new write request would come in, it would find a block that was not used, that was like fresh, copy the data from there to a used block so that was already almost worn out, and write the new data over there. So you would have an extra write operation in between, and that made it terribly slow. Yeah, we weren't quite sure what to do, what the reasons for that were, and so we just called the vendor, switched the disks. Maybe they were already. So sometimes they sell refurbished disks also. So maybe we didn't know how much we actually used of the capacity, and yeah, but with the new disks after 8 months, same thing happened again. And now we learned, we had monitoring, so we knew that we wrote all the data ourselves. So we had to investigate. And yeah, we can try to remember this number. This was the write load we calculated from the petabytes written and our monitoring and the time period. And it was way too much. So we didn't see that much on IOStat, and even the writes we saw on IOStat were too much for that, what we actually updated in the database. So what were the reasons? One reason was the MySQL double write buffer. Whenever we page from the random access memory from the MySQL server is flushed to disk, it's written twice. It's written once to the double write buffer, once to storage. Why? If something happens, the server crashes while writing to storage, then we still have a consistent copy of the data in the double write buffer and can restore it. And of course the other way around. That makes a lot of sense for spinning disks, but not for SSDs, as we see later. Okay, let's skip over. This is write amplification. Yeah, it's basically related to the different block sizes. If I only update one write block in a big erase block array, and all the other data isn't touched, then so the new data is appended at the end, and these blocks are theoretically free. But to use them, I would have to erase all the data because I only can erase big blocks of data. So to reclaim that space, I have to copy the data somewhere else, or the SSD has to, and then can reclaim the free space. It's write amplification, and it happens on the disk, so you don't see the IOStat, for example. Well, then there's insufficient file system support, wear leveling. I've already told you about that. The trim command tells the SSD that these blocks are unused, so it doesn't, like, deleted in the file system is different from discarded on the SSD. The SSD has to know that you deleted the data, you don't need it anymore, so it doesn't have to manage it, copy it around and so on. So we also didn't have that because our kernel was too old. So, and yeah, we asked Fusion.io also to help us with that, so we were the second guys in Europe who managed to write one of the disks to death, so they were quite interested and happy to help us. And yeah, instead of suffering from the weaknesses, we want to leverage the strength of the SSDs. As I'm a little bit late, I just skipped to the one slide that explains it all, this one. So this was our old setup. We had a MySQL server, and it used this double write buffer to write every update twice. In between, we had an X3 file system that just used the regular block layer that was exposed by the SSD. And you see here all the stuff going on here, block allocation, mapping, recycling. So there is a mapping between logical and physical blocks, of course, and the file system does it using this abstract block layer, and the SSD does it using a layer between the physical flash memory and the blocks it exposes. And we don't need this if we use a special file system that is made for SSDs, and it supports two things. It supports atomic writes. So on an SSD, as I append the new data anyway, I can just write atomically. I can, if I do an update of several blocks, I can write them in one transaction. The old data is still there because I cannot do an in-place update anyway. So I can guarantee the application that this write operation is done atomically. So I don't need the double write buffer. And I also get rid of all the stuff over here that the file system does in addition to the flash layer that also does it. And doing that, we reduced the write load about a factor of 3. And also we got new disks because the old one didn't support atomic writes. And so, yeah, it works. So we have dramatically reduced the write load. Also the performance improved because we only write a third of the, we had only a third of the IOPS than before. Yeah, and so, yeah, we're happy with that. And I think that's it from my side. If you have any questions, I think, yeah, just come to me. I think the lightning talks are going to start right now, so don't bother to leave. And so thank you very much.